Good afternoon and welcome back. The plan for today is continuing talking about virtual memory and main memory. Just a quick reminder that this is not part of your quiz two. Uh, for quiz two specifically, we talked about last time what are the things going to be included. I also make a post about the logistics, basically the same thing as last time. So all the same things apply. You can bring 3 sheets of cheat sheets. You're not allowed to use calculators or your cell phone. Exam is in person. If you're CAE students, uh, make sure to contact CAE Center. And yeah, that's it from that. The detailed review of for quiz two will be tomorrow during the discussion sections, 2 to 4 and 4 to 6. Since some of you may not be able to attend, I asked the LAs and TAs to try to record. I think they're going to record the 2 to 4 one probably. So just FYI, if we want to watch it before the quiz, you're not gonna have much time because we're probably gonna release it at like 5 or 6, so you have like few hours before the quiz or the morning of the quiz on Thursday. Uh, any questions? And then we also released the grades for quiz one. Uh, I think we have a few people who actually got the full grade, so congratulations to them. I also posted the stats. If you didn't do well, don't worry because the grades in this class is fairly spread, so you have chance to kind of catch up with quiz two, quiz three, the computer assignments and all that. So there is opportunity to get good grades in the class, even if you didn't necessarily do well in your quiz one. Okay. If you have questions about grading and all, submit a regrade request. We probably close it sometime next week or so. I'm going to announce the exact dates, but check it and then submit a regrade request if you okay? Any questions? Homework is due tomorrow in the morning. Just be careful that it's not PM, it's AM. We're going to discuss the solution during the discussion sessions. Okay? Perfect. So let's get back to the lecture that we had last time. Remember, we were talking about how do we handle the main memory in order to handle different processes. And we said that a simple thing would have been to have a static partitioning and have some form of a bound and an offset. And this way we can make sure that we can easily access. There were like 2 things that we need to make sure: the isolation and making sure that the program works in any other system. So we need to have some form of an offset. But this is not the most efficient way of handling the memory because what if I need to create a new process? What if one process needs to grow? What one process needs to shrink? And so on and so forth. So instead of having that sort of rigid assignments to the memory, we actually divided into smaller blocks called pages. And assign memory in page granularity. So the idea is still sort of the same. Previously, we did it in big chunks and big blocks, but now we are saying that actually these big blocks are not a good idea. So this actually creates a small chunks. For example, you can have 4 kilobytes or 2 kilobytes of continuous memory, call that a page and assign it based on the demand. So initially, each process can get like 4 or 5 pages or whatever number that is required. But then if it needs more, we assign more pages to each process. This way, we always have some empty space in the memory. So if the new process comes, we can create new pages for it. If a process no longer needs a page, we can take back the page and assign it to another process and so on and so forth. And then in this paging mechanism, then operating system or any other system process also becomes a page-based system. So that would be what we're gonna get. The good thing about this paging, system is you're gonna get a lot of benefits, right? But the problem is that we need to now track the location of each of these pages, because now things are scattered. There's no longer that saying that, oh, process one is from this address to this address is one process, this address to this address is another process, and so on and so forth. Now it could be like the first page might be for one process, the next page might be from another process, and so on and so forth. So I need to now know exactly where, for each given process, where are the pages. And for all the pages, I need that, right? So for this, I need some form of a table, some form of a memory to remember and store the mappings. That, okay, the beginning of this page is stored here, the beginning of next page is stored there, and so on and so forth. I don't need to remember all the addresses. Since I know each page is 4 kilobytes, all I need to know is the beginning of that page, right? So I know all the addresses within this range belong to that page, and the same story over and over, right? So I need to store these offsets, this pointers to the beginning of each page, and that would be what I stored in this kind of a memory storage unit. Yes?
So is the basic for the same program?
Yes, each process will have its unique page tag. Yeah. If it needs different pages, it needs a translation for each page. Yeah. So this is called page table. So this table of remembering. So this does not store any content, right? It's just storing the pointers to the pages. The actual content is stored in the memory. This is just telling you where to go into the memory. So it's just storing some addresses. Think about it as some sort of an address book, right? So you check the address book, and then you go to that address to bring the data that you want, okay? Since there is this sort of a translation between the processes and the actual pages, then this gives us a nice opportunity for having what we call a virtual address. Yes, question? We still haven't talked about TLB, right? So for now, TLB does not exist. I'll later talk about TLB. So each page is still 4 kilobytes of data, right? And remember, we still need to have byte addressability. So each page is 4,000 lines, and then you can access any of those lines. Oh, so if you have a blocking, then depends on what is the size of block. Yes. So for example, if cache wants to read something from the memory, it goes and bring 4 of those or 8 of those to create like an 8 block. But we should be able to individually address, or if you want to bring all of them together, we should. Okay. So going back to what I was going to say is that this gives us an opportunity for this thing called virtual address. Why we want virtual addressing? Virtual addressing is very nice and handy when we are writing programs. So essentially, the idea of virtual address is that when we are writing programs, and generally when we are dealing with addresses, when we are within a process, we don't need to necessarily know where each of these pages are. What we can do is that we can start addresses from 0, 0. And we can assume that we have all the addresses in the world and all the addresses are continuous, okay? So essentially each program thinks that it has access to all the addresses, and all the addresses are continuous, and addresses are started from 0, 0, okay? What will happen then, though, is that we will need to translate these virtual addresses to physical addresses. So what we do is we also page these virtual addresses and say that, okay, every 4 kilobytes of virtual address belongs to one physical page, okay? And what we do is that we translate this virtual address, virtual page, to a physical page, and then go and actually grab it from the memory, okay? This is called address translation, from virtual addresses to physical addresses. The reason we call it virtual, because these are actually do not exist in real hardware, right? These are just some illusions that each program thinks that it starts from 0, 0, but then we actually make it physical so that we can go and grab it from the memory, okay? So essentially the life cycle of any address, any access to the memory looks like this, that you start with a program. This program creates some virtual address. So for example, think about like your array A0, A1, and so on and so forth in your program. These will be translated into some virtual address, right? Virtual address 1, virtual address 2, and so on and so forth. These virtual addresses needs to be translated into physical address 1, physical address 2. This is the actual address that we go and grab it from the actual memory. So this will be an actual line in the memory. We bring that data back and then all the way to the program. So that will be the data that we read from the A1. Yes. A1, A0 is your matrix. Like, you have a code, like a C code that is, I don't know, like A0 is equal to X plus Y. I don't know. Like a piece of code in C, C++, in some high level language. All right, so what will happen is that your virtual address looks like this, that you have a bunch of programs, and each program, for example, if your addresses are 32-bit, each program thinks that this is how the memory is scheduled for it. That it has usually, I mean, depending on which operating system you're talking about, usually programs have sections. So for example, it has a reserve section, it has a code section, it has a data section, it has a heap section, it has a stack section, and so on and so forth. Heap and stack usually grow in opposite directions. So for example, heap grows downward and stack grows upward, or other way around, depending on the ISA. And program B thinks the same thing, that, okay, this is my data, this is my heap, this is my stack. I start from, this one starts from address 00, this one also starts from address 00. Okay? The reality is, though, that we have a physical memory. And this physical memory, the number of bits that we have for the physical memory is the actual hardware that we bought. So, for example, you can pay for a laptop that has 256 gigabytes of RAM. You can also pay more and buy and update it to 512 or so on and so forth, right? Sorry, megabytes, not gigabytes. You can get like 32 or 16 or 8. Cell phones is usually lower. So generally, what you have is what you install in the system, right? So it's not like you have 2 to the power 32. You might have more, you might have less. Okay, so there needs to be some form of a mapping between this virtual memory to this physical memory. Okay. You might also wonder that, okay, this doesn't make sense, because if virtual addresses are 32 and then our physical addresses are less, and now I have multiple programs, how do we actually fit this into the main memory, right? The way this works is that this is just illusion, which means that initially, although we technically can have the entire memory, when a program starts, we don't assign all the 2 to the power of 32 to that program. We only assign a small section of this memory. And if it needs more, it will grow. So, for example, if the operating system starts a new process, it will say that, you know what, this is some amount of memory you have for your code section. This is some amount of memory you have for memory section, and so on and so forth. If you need more, I'll give you more, right? Of course, there will be some case that your memory will be filled up. So when, for example, loading a huge file and your computer crashes, it's because it runs out of actual physical memory. But in most cases, the amount of actual memory that you use is significantly less. That's why you can actually load a bunch of these things at the same time. Yes?
So, prefix, like, prefix of data, is the number of bytes prefix for a program for data system?
So you're asking that in this initial assignments, is it same? No, it's different, right? So for example, you might have a program that has lots of data, right? The data section might be huge. For example, you're loading a large static array or something. So in that case, your data section might be big. So that's why, for example, when you're loading MATLAB, it takes 100 years versus if you're loading your, Chrome or whatever, it takes instant because the amount of memory that it loads is different.
Like you said, a prefix, like expand memory, and then you allocate more key, right?
Yes.
Like let's say that what happens if that initial small, like memory slot is not useful, that may be treated like if I learn to feed it.
Yeah, so the operating system is, so the question is about how do we dynamically handle it. So the operating system dynamically handle all of these things. So there is this thing called demand paging that we're going to later talk about, that it can take back or assign more. So all these pages are being handled by the operating system. There is also this process called garbage collection, which is pages that is no longer used, needs to be deallocated. And again, that's a very important process in the operating system. So the operating system handles all of this. It's a little bit out of the scope of this class because we're not talking much about the operating system.
Not perfect.
There's always going to be some unused space, some fragmentation, of course. All right, so for now, let's assume that we have enough for everybody. Later on, I'm going to also talk about the demand paging. And since we also don't forget that we also have much bigger memory, which is my secondary memory. This is my flash or hard drive. And this is usually an order of terabytes. So eventually I can fit all of these programs into here. But at the moment, I only kind of assign subset of these to my physical memory. Okay, so just keep that in mind that your data is still there in the flash, but it's just not everything will be loaded into the main memory. Okay? All right, going back to this, we have this address translation between virtual addresses and physical addresses. Okay? So this is the process and how it looks like. So we have a virtual address that can be, start from 0 all the way to n-1. And then we also have physical address that starts from 0, go to m-1. What is m and n? N is the virtual address size. So for example, I'll tell you that all the addresses are 32-bit or all the addresses are 64-bit. This is the difference between version of the operating system that you have. So you have a 32-bit version operating system or 64-bit version operating system. This is typically the size that n, okay? And what is M? As I said, M is what you actually put into it's a hardware that you put into your system. So if you buy a 16, gigabytes RAM or 32 gigabyte RAM, that's how much you're gonna get. A log of that would be the number of bits that you have. Okay. Then you have this important thing called page offset. The reason that we have page offset is, as I said before, each page is 4 kilobytes of data, for example. By default, most of the modern operating system use 4 kilobytes as their kind of default number. But this 4 kilobytes is not strict. It could be any other numbers. In fact, actually, many modern operating systems has this thing called huge pages, which are usually 2 megabytes bigger, right? So think about block size and block sizing that we had in the cache. Similar idea applies to the operating system and paging. So you can have smaller blocks and bigger blocks. Same idea here. So just for now, let's assume that all of our pages are 4 kilobytes. Since I need to be able to address the memory at the byte granularity, I need to have this page offset, right? So how big is the page offset? The page offset is big as the page size. So if I have 4 kilobytes, I need 12 bits to be able to address different bytes in that memory, okay? What we do usually is that to make things simpler, since the size that we assume for the virtual address and the size that we assume for the physical pages are the same, we use just the same page offset for both cases. So the page offset within the virtual address is the same as the page offset within the physical address. So in that case, I don't need to translate the page offset. I just take the existing page offset and put it into the physical one. That also makes the search much faster. So it's much better to do it this way rather than translate everything because then it's serialized. So I use the page offset directly. This part, which is called the virtual page number or VPN, is going to be translated into this thing called physical page number or PPN. Okay, so the translation is translating VPN to PPN, and I just take the page offset and then concatenate it with the PPN, and that's the new address that we're going to have. Okay. So giving you some examples, let's say the virtual memory size is 32 bytes. So I have 4 gigabytes of virtual memory size. Let's say my physical page memory size is 256 megabytes. That will give me 2 to the power of 28. Let's say page size is of 4 kilobytes. That gives me 2 to the power of 12 bytes. So in that case, my virtual address size is 32 bits. My physical address size is 28 bits. My page offset is 12 bits. That means that the size of my VPN is 20 bits because 32 minus 12. And the size of my physical page are 16 bits or 2 to the power of 16. Any questions here? So how does this page lookup or page translation look like? The page translation looks something like this, that think about this is your page table. Okay. So this page table, think about it as an array. That's this virtual page number indexed through that array, right? So if I have, for example, 2 to the power of 20, there is a 2 to the power of 20 different entries within this page that you can address it with the VPN. So if VPN is 0000 all the way to 20 bits of 0, you address the first one. If it's 10000 all the way to 20 bits, it's the second one, and so on and so forth. So the VPN index into this table. Inside that table, you have a number stored, and that is the PPN. That's the physical page number. So the storage in this case, for example, in this example above, is that you store 16 bits number here, right? So inside each of these entries, you have the PPN, and that's the number that you stored there. You read that value, you concatenate it with the page offset, and now you have your physical address. Okay? So that's how you translate an address. It's just a massive table that you index through it. You bring the data that you want, and you will have your address. Any questions here? Yes.
Is it the same way or like all its bits? That's it, or it's the whole?
No, it's the whole thing, right? So as I'm saying, there's an entry per each VPN, right? Eventually, it needs to be an entry for each VPN because we need to address all of them. Later, we're going to introduce caching and all that, but for now, just a massive thing. Yeah. Per program, yes. So this is per program. How the program knows which page is this is, I have it somewhere. So there is this base register, okay? That this base register is per process. So think about this as even bigger table that let's say you have 10 programs. So 10 times 2 to the power of 20. That's the big size of the page table. The base is basically telling you where it is. So base program 0 is base 0. Program 1 is 2 to the power of 20 plus 1. Program number 2 is 2 to the power of 20 times 2 plus 1, and so on and so forth. Yeah.
If we have more bits for but does not mess up.
If we have more bits for PPN than VPN? Yes, we have more bits for VPN.
So that they all can.
If it can be 1-to-1, then you still need the address translation because you have multiple programs. What happens to the extra VPN bits? So you're gonna later see that essentially not all of these VPNs are actually assigned. So you're not gonna have, yes, if you have more VPN than PPN, you cannot fit it into this memory and your program will crash. Okay. Later on, you're going to see this demand paging that if I have more VPNs, I store some of it inside the main memory. I store the rest in the flash, and I swap them. but in reality, you're not going to have VPN assigned. So you technically can have this many VPNs. In reality, you have only a small portion of them. Any other questions? Yes, and as I said, there is one entry for every address, technically, okay? So you can, if you want to, you can address any VPN that you want. And then, as I said, in order to swap between the processes, you just change the base address. So this is usually the responsibility of the operating system, that when you're context switching between programs, one of the things that happens during the context switching is that the base register changes from that program. So then you go to the next program, the base addresses changes. All the addresses now is based on that. That's the nice thing about using the page tables. Okay. What do we store in the page table? This is called page table entry or PTE. It's not the PTEs that you like. It's the PTE. It's different. By the way, submit an ECR if you want to get into 115C. I don't issue PTEs right now. But going back to this, table entries, what do we store in the page table entry? Is, as I said, main thing that we stored in the page table entry is the PPN, the page physical page number. For example, in the example I gave you, this is 16 bits, okay? But usually inside each of this entry, we store a lot of other things, lots of metadata or flags. What are these flags? These flags are for example, showing that whether the page is readable or writable. Whether this is modifiable by a particular other process, whether this is shared among different processes. Is it executable or is it just read-only? So there are a whole bunch of these different things that the operating system can apply here. And this could be a sequence of flags. So like zeros and ones that I can store here. And there could be many of them. Okay, so for example, it could be 4 or 8 or in different operating systems, there's many different things. Okay, this is actually where that we enforce the accessibility of each of the pages. Remember, I told you that program 1, for example, should not be able to access the addresses of program 2. This is how we are actually enforcing that. For example, each page has an owner, right? So, for example, this page of the first page, the owner of the first page is process 1. So if the request is coming from process 2 and trying to access this page, when we are translating that address, we don't translate it, right? So we block the request, and the processor the process cannot do anything because it doesn't know the address, right? So that's how we enforce this isolation mechanism that we want. How do we share pages between the processes? Again, this is where we're going to share the pages. That we, for example, say that this is shared with process number 2. So process number 2 can also read this page and so on and so forth. So all of those enforcements actually happens during the address translation by storing proper flags here. So it's very important that we protect our page tables from being modified by an adversaries and so on if we want to maintain the security. Okay? All right. Any questions here? So the big question though is where do we store the page table? Because page table is this massive thing, right? So it could be potentially gigabytes of data. So we need some form of a storage mechanism for that. And where do we store that? So the answer to that is that we use the memory itself to store the page table, okay? So what does that mean is that any actual memory address is in fact 2 memory accesses. The first memory access is just accessing the page table because I need to actually go and read the page table. The second access is when the address is known and you go and actually grab the actual physical address. Okay? So when I have this address translation thing, each access to the main memory is technically 2 accesses. First one to the page table. Second one is that now that I have the actual address and I go and grab it. Okay. let's also think about like how large is the page table. So I told you that, for example, in the example I gave you, we have 2 to the power of 20 virtual pages. I have 2 to the power of 28 physical pages, which means that now I need at least 28 bits for storing the page PPN. Let's say we also have bits and flags and all those stuff. Let's say, for example, approximately we need 32 bits per entry in the page table. This is adding lots of other flags and all. I'm just making some approximation here. Okay, so that means that I have 2 to the power of 20 times 32. This is roughly 4 megabytes per application. This is the size of the page table itself for one application. If I have 10 of these applications, that's like 40 megabytes of data. So 40 megabytes of my main memory should be just dedicated to just storing the addresses, not even the content, just the addresses. Okay? And then this thing absolutely gets worse if you have the 64-bit version, because the 64-bit version, now I have even more VPNs. Okay, so just keep that in mind, that how massive this storage is. Okay, so this brings the question of, do we really store 4 megabytes per applications, or are there ways to make this more compressed? Anyone wants to give any suggestions of how do we compress this? So we're going to do this called hierarchical page table. So essentially, we store a page table of that page table, and we do this as recursive as we want in order to reduce the number of storage that is required. Okay. So how does it work? So essentially, the idea of hierarchical page tables is like this: that we have, instead of like taking the entire address, right? Remember that originally this was your VPN and you were indexing in a table of that size. What we can do is that we can, let's say, have two layers of two levels of page table, level 1 and level 2. And then we divide the address, let's say the 20-bit address that we had, into level 1 and level 2, okay? So for example, I use the 10 upper bits, the most significant bits, to index through level 1. And then I use the next 10 bits to index to level 2. So how does it work? So I have a base pointer that basically points to the beginning of the first level. As I said, for each process, for each program, we have a base pointer for that. Operating system remembers those base pointers. I don't need a page table for that. So I know that base pointer, so I know the beginning of this first page table at least. Then I'm going to use P1 to address and index through this first level of table. Okay. For example, if let's say I only have 4 of these, let's say if this is just 4-bit, this is just 2 bits, then I'm going to only have 4 entries. So depending on that number, I'm going to index. So let's say that the number is like 10. So I index and grab this. What do I store there is not PPN, is the base of the next level of VPN. Okay, so this is different. So here I'm not storing PPN yet. I'm storing the second level VPN. Okay, so this will be the base pointer to these page tables. So since I have, for example, 4 entries here, I have 4 groups of level 2 tables. So this one, it basically points to here. Then I'm using P2 to index through that. And this is where I'm going to actually have the PPN. So this is my PPN. Okay. And then using the page offset, I'm going to address the actual physical memory to bring the data that I want. Okay. So there are a lot happening. So let me repeat. So what I'm trying to do is reducing the amount that I need to store as the page table. The idea is that the same way that we did page tabling, we use a page table for the page table. This is called hierarchical page table. In modern systems, this could be 4 to 8 level of page tables. Here I'm just showing you 2 level. So the idea is that I take the VPN, in this case, this is a 20-bit number. I take that and divide it into 2 pieces, a 10-bit and another 10-bit. The first 10 bit is used to index through the first level. The second 10 bits is used to index through the second level, okay? So I do this process that I take the first index, I index through the first page, that will give me the base pointer of the second table. I go through that second table and then I use the second level index to index through it, and that gives me the actual PPN, okay? So going back to one memory access was technically 2 memory accesses. Now one memory access is technically 3 memory accesses, right? I need one access to read level 1. I need one access to read level 2. I need another access to actually read and bring it from the actual physical memory, okay? So looking at this is, by the way, called walking. So you're walking through this hierarchical page table. You kind of like start from here and you go like this. So kind of walk through the part of the memory, different parts of the memory, okay? And as I said, this walking could be up to 8 stages of reading different levels and levels of memory, just FYI, okay? So let's see, how does this help actually? By first glance, this doesn't not only helps, but it actually increases the size. Why? Because if I assign everything in page level 1, I then need like a big page table for level 2. So if you actually plug in the numbers, you will see that this is much, much bigger than the 4 megabytes that I initially set. Okay? But where does the benefit is coming from? The benefit is coming from the fact that virtual address is very, very sparse, especially in the upper bits. What this means is that if I look at this upper 10 bits, in most cases, it's either all zeros or like 00001. What it means is that really the first 2 or first 3 entries are actually valid entries. The rest of it is empty. So I don't need to even assign a level 2 page table for these unused bits, okay? So in reality, what will happen is that your page table looks something like this, that some of the level 2s are assigned, many of the level 2s are not assigned, okay? So you will get a lot of benefit in terms of storage because you don't need to store many, many level 2 page tables. All you need to store is one level 1 page table and some level 2 page tables. And again, if you plug in the numbers, you will see that, for example, if half or more than these pages are zeros, then you're going to actually have a much, much smaller page tables. Okay? So again, where the benefit is coming from is, especially in higher bits, you're not going to use it, because remember I told you that virtual address is to start from 00 and you grow as you need. Most programs are small programs. You don't want to use higher bits of memory anyway. So those level 1s, or most of these entries here, are empty. They're not assigned to any actual physical address. So you don't need to assign these tables, because this one, for example, points to this one. This one is pointing to this one. This one points to this one. So if this address is empty, this address is empty, you don't need this table, you don't need this table. So you don't need to store them anyway. You only store them when you actually assign something to them, okay? So as a result, what you're actually storing is much, much less than what you think you're storing. And the overhead of the page table is less. Then you can actually do it multiple. The reason that you're actually having multiple levels is, again, benefiting from this even more. So saying that, okay, the first page, I not only don't need to assign level 2, I also don't need to assign level 3. But then, for example, if there is some sparsity in level 2, you also don't need to assign some of these level 3s, and so on and so forth. So the more sparse, the more benefit you get from this kind of hierarchical way of applying this address space. Yes.
So extension here, turn back.
Level sparsity. Yeah. So you introduce granularity in order to achieve to benefit from the sparse. But yeah, it could be totally possible that you need all of those addresses. And if you do, you're paying a lot of penalty, and that's okay. So your system should be able to support that. But what I'm saying is, in average case, in majority of the applications, you get benefit. So just keep that in mind. Any questions? Oh, yeah.
The more granular, the less wasted memory.
The more granular it is, the less wasted memory, but the overhead is more accesses, right? So it takes much more time to access an actual page if you have multiple layers of hierarchy, right? So if I only have one page table, it's one access. If I have two levels, it's two accesses. If I have four levels, it's five accesses, and so on and so forth. So that's the trade-off. Okay? So kind of like to summarize, we introduced the notion of hierarchical page tables. Essentially, since we need page table for address translation, and this page table itself needs to be stored in the memory, what we do is that we use this hierarchical way to leverage the existing sparsity in virtual addresses in order to store less page table mapping. Okay, because less storage for page table means that I can use that storage for actual useful data, because page table data is completely useless in terms of content that you're storing, right? So that's why we want to compact this page table as much as possible. Okay. So now let's go back to the first thing that I was saying. So we can compact the page table as much as we want, but it's still a big problem when we are introducing this virtual address, and that is every axis now is multiple accesses. If you only have one level of page table, I have two accesses, one to the page table and one to the main memory, right? And you already know how slow access to the main memory is, right? So, and now I'm telling you that that's double, actually, in fact. So in terms of the processor's stalling cycle, that's many, many stalls. And that's what I don't like about at all. So I don't want to stall my processor. So we need to do something to make this address translation as fast as possible, okay? What should we do? Any suggestions? How do we make the address translation fast? Yeah. A cache of what? Yes, you can actually cache the recent translations. So instead of going to the memory and bring that page table, it just immediately has access to the translation. Did you add something else to add? I think that's the same thing. Any other suggestions? Yeah, so caching is actually the answer. So what we can do is that we can cache the most recent translation, and that's the TLB that you were suggesting. This is called translation look-aside buffer. So it's some form of a buffer that what it does is essentially remembering that for this given VPN, what was the PPN? Okay, let's say I have, for example, 8 entry cache. So what I remember is in this buffer is a group of VPNs and PPNs, and say that, okay, VPN like 1,232,000 was mapped to PPN, I don't know, 232,000, something like that. So some numbers. Next time I have an access, I first search through this TLB, okay? So the access that comes from the CPU, the first thing that you do is looking into your TLB. You see that for this given VPN, do I have a recent translation for it? So I search through this TLB and see whether I have a VPN PPN match. If I do, in case that this is called a TLB hit, then I have my physical address. I don't need anything else. I don't need to walk. I don't need to access page table. I already know my PPN. That's great. I add my page offset and boom, I have my physical address. So this is called TLB hit. And this is my physical address. And now I can go to the cache, I can go to the main memory and all those things. Okay. And by the way, all the addresses are physical addresses. All the addresses at the CPU side are virtual addresses. So this translation, it needs to also happen at the cache level. Okay. So this actually happens in this unit called Memory Management Unit, or MMU. Okay. So MMU is responsible for this virtual to physical address translation. Just keep that in mind that not all the processors have an MMU. So many processors actually directly talk to the physical address. So embedded systems, systems that doesn't have operating systems, low-end processors directly talk to their cache or to their memory without the translation. But that means that they cannot have the nice things that the operating system has. They cannot dynamically add and remove programs and everything else. So for example, if you deal with like Arduinos don't have MMUs. They just have like a rigid memory. Every address is a physical address. But in most modern systems, including all the phones and laptops and servers, you will have this MMU that does the address translation. What does it do? First checks the TLB. If the address is there, you have your physical address. You don't need to be worried about anything else. If it's a miss, it's called a TLB miss. It means that now I need to go to my page table. I need to walk. I need to bring that data to and have that translation. Then I can go to my physical address to the cache and all that. So there is a huge difference in terms of latency between accesses that are TLB miss versus the accesses that are TLB hit. Because TLB miss means that you have to go to the main memory and bring it, versus TLB hit is just looking at that TLB and that's it. That's as fast as possible. Yes.
Stores the map.
The TLB stores the mapping between PPN and VPN. Yes.
Essentially, instead of those memory, there's still one memory actually.
No. This TLB is usually on chip, so it's like a register file.
Yeah, what I'm trying to say is, if there's a TLB bit, you still have to go to memory and treat the memory doesn't want to work, right?
What TLB gives you is the physical address. Now the question is, where is that physical address? It could be in L1, it could be in L2, it could be L3, it could be main memory. So that part we're not fixing, right? You're not storing the content, you're just storing the mapping. Because in order to store the content, I need to store 4 kilobytes of data, which I don't like.
Good. I'm essentially trying to VPN, if it's a bit, you essentially know where the data is.
Yes.
You
go directly and bring it. It could be L1, it could be L2, it could be main memory.
It's amazing.
Yes. If it's a miss, you have to traverse.
Do you like modify the TLB like
yes, you usually modify the TLB to do that. I'll actually talk about how to maintain TLB. But before that, one important thing is that now you need to realize is that your actual hit time from the CPU perspective is not just L1 cache, it's actually TTLB plus TL1. So in best case scenario, where your mapping is inside the TLB, so it's a TLB hit, and your data is in L1 cache, the fastest that you can retrieve this data is TTLB plus T of L1. Okay? So T of L1 is usually 1 cycle. You usually design TLB to be as fast as as L1 cache as well. That's usually also 1 cycle. Okay? So you cannot retrieve things faster than 2 cycles when you have address translation. Okay? Yes. Page tables are page tables are like calculated like this. So there is a base pointer that is provided by the operating system, and then you take this address and go to that to that address to bring that value. So those offsets are actual base offset inside the mem, the physical mem. It's all of it is physical memory. So these tables are also part of this physical memory. The reason I'm differentiating between them is those physical memories is where I'm actually accessing, storing the actual content. This is just for the page table. But yeah, all of it is physical memory. There's nothing but physical memory in our system. So this is how our page table would look like. So essentially the VPN comes. The VPN first goes to, yeah. So when you're first accessing the page table, so the question is that what is this address? So this address is provided by the operating system and is an actual physical address. This is the offset to that address. So this is where you actually store things inside the physical memory. Okay? Mm-hmm. But then from here on, these are all physical addresses stored, right? Okay. So here's the timeline. You you essentially cache the recent mapping, right? So you have an address, you have the VPN address, similar to caches. You use the tag to remember what you have stored. The tag could be just the VPN number itself, could be lower bits of VPN number, and so on and so forth. Then you take the PPN. And if you take the PPN now, you have your PPN, and then you can basically add the offset, and you have your physical address here. If you don't have, if it's not a hit and it's a miss, then you're gonna walk the page table to refill the TLB and also providing the physical address. Okay. So how big is the TLB? Typically, TLBs are ranging between 32 to 128. They are fully associative because pages usually don't have spatial locality that much. So you want to search through the whole thing. Uh, um, uh, Larger page tables are also possible. If you go beyond 128, then you can make a set associative design. You also might have multiple levels for TLB. So you can have L1 and L2. So similar that you have L1 cache and L2 cache, you can have L1 TLB and L2 TLB. And important things about TLB, and by the way, the replacement policy is usually either random or FIFO, because again, spatial and temporal locality is less of a thing in TLBs, but you can technically also implement LRUs and all those things if you want to for TLBs as well. Nothing prevents you from doing that. Important things about TLB is that if I store all the continuous addresses that I can, how much of a virtual address can I support? And this is usually called TLB reach, okay? So TLB reach means the number of entries times the size of the page, okay? So for example, if you have 64 entries and each page is 4 kilobytes, my reach is 256 kilobytes. That means that this is the contiguous addresses that I can store in my go on my TLB. Why this is important? Because in many applications, in many big applications that you kind of like go one address after another, having like a good reach helps you to reduce the number of TLB misses, right? So essentially, if your program is less than this, you kind of can guarantee that you never have TLB misses, right? So that's important to have a good TLB reach, especially for big applications to get the most performance possible. Handling TLB is done by the operating system because page table walking is done by the operating system. So when we want to fill the TLB, the operating system does that for you. Okay. And as I said, this whole thing, where the TLB is implemented and how this TLB miss and hits are handled, it's handled by this unit called MMU, or Memory Management Units. Okay? And then if it's a TLB miss, this will cause what we call an exception, which means that your process is halted. You handle this exception in order to go and bring the data. So this will cause a huge number of cycles in terms of stalling for the processor. So TLB miss is actually very, very negative things in terms of performance for your system. Okay? But TLB misses are very rare. Think about, like, you have 4 kilobytes of data in just one page. So many accesses are actually fall within one page. And the first time you translate it, after that, all the accesses are within the same page. You have it in the TLB. So once, if you do byte by byte, once every 4,000 accesses, you're actually having a TLB miss. So the number of TLB misses are not that high. Okay? All right, so let's have a quick break here. We come back and talk about the disk as well. Tomorrow. Quiz review tomorrow. All right. Oh, no. Okay. Moving forward. So we talked about main memory and told you that I have a physical memory that potentially could be much smaller than your virtual address space. And even worse, you can have a physical memory that's much smaller than all the applications, because you might have 20, 50, even 100 different processes for a given computer or for a given system. So where do we actually store these things if we only have 2 to the power of 28? Where do we store these things? As I said, we store them in the disk, because disk is massive, right? So your disk could be terabytes and terabytes of data. Of course, your disk also can at some point get full. That's when you cannot assign any more programs, or you cannot download any more data, because your disk is full. So you cannot have data that you never stored before, right? So if you cannot load new things, when your disk is full, you cannot load new things. Okay, so that's kind of like, straightforward and given. But you have all your programs at least stored in the disk. Okay, so now the question is, how does the disk talk to the main memory? Like, what does the process look like? Important thing is that the good thing about this is much larger. Bad thing about this is that the access time to the disk is really, really high. Okay, orders of magnitudes higher than the DRAM, and DRAM already is pretty slow, right? So we are talking about really, really slow. The way that we handle this is this thing called demand paging or page swapping. Okay, so the concept of pages that we explain and show you how to do the mapping and translation, that extends to the disk as well. So we store things in page base in the disk. The difference between disk and main memory, though, is that any page that you want always exists in the disk. Okay, so it's not like you go to the disk and that page does not exist. Okay, so how do we handle things? So we handle things by essentially making the main memory or the DRAM analogous to the cache. So cache and main memory, essentially this is similar to main memory and disk. Okay, so remember that, for example, there were blocks that exist. So we always say that all the blocks always exist in the main memory and some of them exist in the cache. Same story here. Some pages exist in the main memory, while all the pages exist in the disk. Okay? Yeah.
So page table is not a table.
The page table, what?
So the page table is not a table.
The page table contains all the pages, but not all the pages are stored in the main memory. So the page table is just a mapping, right? So as I said, for example, if you have 2 to the power of 20, you have 2 to the power of 20 entries. But if you have limited physical addresses storage, you store hopefully most of the pages in the main memory, but the spills, the extra pages that you cannot fit in here, they're all in the disk. Okay? So essentially what will happen is that if I need new pages, I swap them with the existing pages into my main memory. So my main memory has list of pages already. It's already filled. And now I realize that, I actually need another page, and this page does not exist into this memory. So what I do is that since I know that this page exists in the disk, what I will do is that I'll ask operating system to swap this page. So it needs to pick one of these pages, for example, this page. It will kick this page out and bring this page inside the main memory. Okay? This is what we call demand paging. So the application demands the page. The operating system sees whether or not that page exists in the main memory. If it does, then that's great. If it doesn't, now we need to actually go one level lower, bring it from the disk, and put it into the main memory. Yeah. So usually programs are having multiple pages. So a program is much, much bigger than one page. Okay, so each program has tens and tens of pages. So when we are saying the page is not there, it means that for that particular program, the page is not there. We need to go and break it. Oh, on the disk, how do we store things? Yeah, you can make it continuous. Yes, you can make it continuous. How exactly you store things might be different, but you usually also have like sectors. So depending on what technology you're using, some flashes have. Yeah, you can also decide on how to store things to retrieve it as fast as possible. All right. So essentially, you can think about memory as M. But in reality, memory has C byte stores in the DRAM, and C is usually much, much smaller than M because this is usually much bigger than your DRAM, right? So you hopefully can store most of the things that you really want in DRAM. Reality, though, is that there are pages that are not in DRAM, but they exist in the disk, okay? This process that you want a page that you want to read a page and that page does not exist in the DRAM is called page faults. Okay, so TLB miss was when you don't have the translation, and we said that for TLB miss we need to walk the page table. The additional concept is called page faults. Page faults is when the page that you want is not in the DRAM, but it's in the disk. So what you need to do is that you need to ask the operating system to go and grab it for you. Okay? And you bring it from the disk to the main memory when demanded. Okay? So how does the page fault works? So remember that I told you that there is a page fault, there is a page table like this that has the entry, which has the PPN. We usually introduce a column called valid. And this valid basically keeps track of things. If valid bit is 1, it is stored in DRAM. If valid bit is 0, it's not stored in DRAM, it's in the disk. Okay? So when we are actually doing the address translation, and when we go to the page table entry, we check this valid bit. If the valid bit is 0, that will result in a page fault. Operating system will take over. It go and grabs that page actually from the main from the disk, bring it to the main memory, update the page table, give you the results, and you move forward. But that takes thousands and thousands of cycles, just FYI. So page faults is really, really a slow process. Yes. Yeah, there are ways to predict the page faults, but generally keep in mind that accessing the actual physical accessing of the memory is slow. So knowing that, for example, you will have a page fault or not, even if it saves you 2 cycles, 3 cycles, not that beneficial because we are talking about hundreds of thousands of cycles, right? So two, 3, or 10 more cycles is not going to give you, like, it would be 0.001% or something, right? All right. So there might be also the question that, okay, how do we decide? Yeah, question. When the valid bit is 0, page fault happens, which means that I didn't store this in the DRAM. Yeah.
It's much volatile. In this case, for replacement policy, also required to replace some of the unused or like not used pages back to the DRAM and back to the disk and bring some new pages I need to copy.
Yeah, exactly. So the question is, how do we actually handle the demand paging? What should we store in DRAM? What should we store in this? What should we do on the miss? Should we bring the new page? Should we store it? So all those questions that we ask for the cache, to some extent applies to the DRAM, right? So in the cache, we ask questions like, should we bring the block or should we leave it in the main memory? Should we update it and put it as an MRU or should we put it as an LRU? Should we be proactive and prefetch things, or we shouldn't touch it and let the CPU decide when to access things? All of those questions applies here as well. Okay, so how to evict, what sort of replacement policy should be used, and all those things. And in fact, there's actually there is a lot of work in this space. So there is actually a lot of things that are happening. There are two important things that you just need to pay attention. First is all of these things are handled by the operating system rather than hardware. In cache, you implement everything in hardware. The reason for it is that you want things to be very, very quick because you cannot afford thousands and thousands of cycles just to make a decision. Your LRU bits was in hardware. Your replacement policy was actually implemented in hardware. The reason for it is that delays in cache is 1 cycle, 2 cycles, 10 cycles. So we're talking about nanoseconds and picoseconds. Delay in main memory and disk are in millisecond and hundreds of microsecond range. So your operating system can actually implement these things reliably within the time frame that it needs to. Okay? That's why we don't bother by changing the hardware for these things. Everything is actually implemented. So there is literally an LRU way of managing the caches in the operating system. Some of you might have actually implemented it in your course projects. So it's already fast enough for doing things. You still have the same trade-offs, such as, for example, if you do LRU versus pseudo LRU and all that, but just generally operating system is handling that. That's one big difference. The second big difference is the locality. So the locality at the page level and at the disk level is very different than the type of locality that you see at the cache level. You still have some locality, but that locality is slightly different. So just keep that in mind as well. Different ways of things that happen. Okay. But other than that, I'm not going to go through the details of that. That's for an operating system course of like how do we handle the paging and demand paging and all that. Principles are very, very similar to the cache, but we're not going to go through the implementation of those because that's not the scope of this class. Any questions here? All right. So this is kind of like the updated picture of our design. So now I'm also adding the disk. So essentially when the address comes, it first goes through the memory management units to be translated. The first thing that we do is we check the TLB. If the mapping is there, it's a TLB hit. So we already found our physical address. We go to the levels of cache. either it's there or it's inside the main memory. We get our data back and we move forward. Okay, so that's option number one. Option number two is that it's not in the TLB. So we go to the page table and we check the page table. Here, there is also two options. Option number one is that the data is inside the page table. That is, this valid bit is equal to 1, which means that the data is indeed inside the main memory. So we go walk the page table, we find the address, and we move forward. Okay? And option number three is that data is not in the TLB. It's also not in the page table, which means that the valid bit is 0, which means that this data is actually in the disk. So we have to go all the way down to the disk and bring this data back. Okay? This one called TLB hit. This one is called TLB miss. This one is called page fault. So you can have a TLB miss and a page fault at the same time. Okay? Yeah.
So page tables or
the page table is stored in the memory. Yeah. The only thing that is stored in MMU is the TL. All right. Any questions? Great. All right. One last thing before we finish the discussion here is, remember I told you that access time with this system is at best T of TLB plus T of L1, right? So I said that if everything goes well, that you have a hit in TLB and you have a hit in L1 cache, that's the time you're going to get. And say that if I design my TLB well, that would be 1 cycle. This would be 1 cycle. This also will be 1 cycle. So at best, I can get 2 cycle latency, even if the data is in cache. Now the question is, can I make this better? Why I really care about this? Because majority of my time, I'm accessing things in L1 cache. So if I design my memory hierarchy well, I will have hit in my TLB and I'm going to have hit in my L1. So I really, really want to make that 1 cycle go away. So make it 1 cycle still. So the minimum possible, which is 1 cycle. So how do we do that? So essentially what we want to do is somehow parallelize or access L1 before the TLB, right? How can we do that? The first thing that comes to mind is if L1 can somehow be accessible by the virtual address, we are good to go, right? So if address translation is not required by L1, then we don't need the access to TLB. But there is an obvious problem here, right? What is that problem? If I just use virtual addresses for accessing L1, what's the problem I'm going to get? Yeah, try it.
There's going to be some issue accessing data, actually not
Yeah. Yes. So think about 2 programs. Remember I told you that each program thinks that it has access to all the addresses? So what will happen if program 1 thinks that it wants to access address 1000, virtual address 1000, and program 2 also wants to access 1000 in their own programs. These are 2 physical addresses, but from the virtual address point of view, both of them are 1000, right? So this is what we call aliasing, that the 2 virtual addresses are the same from 2 different programs, but their physical addresses are indeed different. And if I just access the cache by virtual address, I'm going to have the aliasing problem, okay? So I cannot do L1 before TLB, but what if I can L1 and TLB in parallel? So That way it would be the access time would be the max of TLB and L1. How do I do that? I'm going to use this concept called virtually indexed physically tagged cache. This is called VIPT, okay? And this is actually all the modern systems use VIPT. So what is VIPT? Remember I told you that we have the page offset, and page offset is not translated. So we use the same page offset for virtual address and the same page offset for physical address. So here's the trick that we are going to do. We are going to say that if my page offset is all I need to index L1, so L1 is small enough that the size of the index is within the page offset size, then I can just take the page offset and index the cache and bring the data, okay? Then what I'm going to do is that in parallel with this, I'm going to take the VPN and look through the TLB. I'm going to get my PPN. Since I've already read my data and tag, I can compare this tag with the PPN because this is the actual physical address. I can extract the tag from the physical address, right? So I compare the tag I stored in the cache with the tag that I extract from the physical address. If these two match, it means that I can access, this is the correct data, right? So, and I already have the data, right? So essentially, by doing these two in parallel, I'm saving a lot of time because in the past, without this, the process was like this, that I access TLB, I get my PPN, then I take PPN and access L1, and I get my data, right? That's why this was one cycle, this was one cycle, so the overall was 2 cycles. What I'm saying now is use the page offset and index L1, use the VPN to access TLB. At this point, you will have 3 things. You will have your data, you will have your tag, you will have your PPN. You can extract tag from the PPN. For example, let's say that higher 8 bits or higher 20 bits, whatever. You compare this tag and see whether this is the same tag that you read from L1. If it is, then you have your data. If it's not, then it means that the data is not in your L1 anyway. So you have to go to L2, L3, and so on. But at that point, you have your PPN. So this one actually goes to L2. Okay? So this way, basically, my hit time becomes the maximum of these 2 parallel search. So this one and this one. Whichever takes more time, that would be my hit time. Usually that's L1 because L1 is slightly bigger than TLB. So I'm still going back to the hit time of my L1. Okay? Any questions? Yeah. Why are we indexing? So the question is, why are we indexing from page offset? Because page offset is the part that I don't need translation for. So I don't need to wait for the TLB for this. This is just directly used in my virtual address and my physical address. Okay? So I'm assuming that if my index and block offset fit into this page offset, then I'm good to go. I don't need translation. Yeah. Say it again. No. So there could be many. So the question is that is there one page in the L1? No, there could be many pages, but it's one page offset per L1 cache. Right? So there is one page for a given page offset, you will bring one block of the cache. The tag might be for this page or it could be for many other pages. You compare that tag to make sure that this is indeed for the page that you store. Yeah.
Let's go with 1, 2.
So think about this, right? So these are your addresses, right? Each address has a unique page offset. You use that to index the tag. If it has the same page offset, it will be a conflict. So it will be a conflict in the cache. How do we fix the conflict? The same way that we fixed the conflict in the past. Either you set associative and all those things. Okay? So it might be a conflict. It might kick each other out and so on. But for a given page offset, we know exactly where it is. You have a question? So the question is, how do we make sure that we bring in the right data? That's why we actually do the comparison between PPN and TAP, right? So we check the actual physical address because things that are stored here are based on physical address, right? So at the end of the day, we check the physical address to make sure that these are the match. If it's not a match, then it's not in the cache. Yeah, you bring it from the page offset. If you make the correct decisions, then you save time. If you didn't, then that's fine. There is just one limitation, and that is the size of your cache should be somehow that this fits into it. So if you have many, many rows, and let's say this is 12 bits, if you have many, many rows that requires more than 12 bits to index, then this would not fit. So you need to make your L1 essentially small enough that it fits within this page offset size. Okay? So that's like one major thing that you have to consider when you're designing this. And it's not just the number of rows, associativity also plays a role. So you can have longer associativity with lower number of rows. So that's how you can actually increase the size. Okay? And as I said, many systems do not have MMU. So just keep that in mind that address translation is very time consuming and very power hungry. So not all the systems have MMUs. Many lower end processors do not have MMUs. Second thing is that many systems do not have a secondary storage. It's just one storage. So the swapping and all is only for systems that have multiple level of storage. Okay? All right. So that's it for this. I guess we have a little bit of time. You know what? We can actually end early today so that you can work on your quiz. And then we're going to start talking about the next topic on Tuesday next week.